Good morning. Here we are going to discuss about my PPT of investigation reinforcement learning. The contents that I have discussed here is the taxi problem, cardboard problem, and the comparison between both of the problems. The taxi problem, the main aim of the taxi is to pick up the customer and drop off the customer from one location to another location. So the destination should be correct. Here we have got four possible directions for a taxi to move. That's north, south, east, west, and the pickup location and the drop off location. The aim or the goal of the taxi is to have a correct destination as soon as possible. The taxi V3 environment is with the OpenAI Gym environment. There are 25 locations, 6 space. State space is 500 possible, so that's 5 into 5 into 5 into 4. There are 4 set destinations during this problem, so that's we discussed in the previous slide as well. So there's north, south, east, west, and pick up in a drop off location. In this problem there are rewards and penalties as well. So a taxi gets rewarded whenever it drops off and picks the customer to a right location. So the location should be correct for the rewarding, and then it will get 20 points. Also, whenever a unique reward is awarded, the taxi gets trained. If the drop off and pickup location is wrong, then it will reduce the -1 point. We have used a random policy here. So the brute force action takes random actions till the customer arrives to the drop off point. This algorithm is not effective because it takes so long, and the agent also did not improve anything from the experiences. So we resulted here that the random policy is not effective because it takes so long and it has extra steps to reach to the destination. It has high penalty rate as well. So these are our 4 locations here. That's the drop off, that's time spent, that's state, that's action space. We got 5 here, rewards we got 20, time steps taken 2485, and the penalties we got is -832. Now we have used Q-learning. So it is an algorithm based on reinforcement learning. So it is the best solution. It is better than random policy. In this, the agent learns from previous experiences, whereas in the random policy, the agent did not improve anything. So here, the random actions could be awarded over the path and Q table changes. Agent gets trained, and also in the Q table, the Q value gets updated. So the Q table tells the agent whether to choose which route. So the route should be smallest and the fastest, so that the agent can earn so that the taxi can earn the maximum points. So here we have got the Q table that has the initial value set to 0, and then the Q values got updated as the agent gets optimal transversal through the environment for the maximum rewards. For the iteration, we got a good Q table that has initializing Q values, choose an action, perform action, measure reward, and update Q table. So there are some the steps to take. Here in the taxi problem, we have got one mathematical equation that has alpha as a learning rate, gamma as a discount factor, max Q as the maximum value of Q from the future states, and this equation updates the Q value. Here we got the cart pole problem, which means that the pole is attached to an unstable cart. So the pole is not attached, it's unstable. We have to keep the pole straight even though the force is applying from any directions. It could be from left, right, top, anywhere, any direction. The game will only end, or the environment will only leaves if the cart pole turns more than 15 degrees or after 2.4 units. In the cart pole problem, the random policy. So that's the random action from action space. This is better, the random space here is better than in the taxi problem, because an award is for the right step. The carpool agent did not improve from the past experience, same as in the taxi problem, so that's exactly same. It runs as many as times the user wants. The graphical representation that I have got here for random policy is there we can see the points did not cross 75. So the maximum point here is 75. We can just get the average that it doesn't cross 100 points, and then points stay up to one time over time. So it will just stay up to 75 over a one time. We go equation, mathematical equation used in the Q-learning, that's this one. And what it does is it updates Q value in the Q table after each move. After each move is made, if it's passed, then you get plus 1 point. If it's failed, then you will minus 375 points. It increases the chances to get more rewards, and also the training makes more rewarding actions. The Q-learning has the graphical representation that shows that has a positive trend. So that's better than the random policy because it's keep on increasing. We can see the positive factor here. So that's effective than the random policy. Agent gain experience here. We got the comparison now. So what we can compare here is the taxi problem and the carpool problem. So the taxi problem has action space more than 2, so that has more action space options than the carpool problem, but the carpool problem only has got just 2 options. The state space is much more longer, and random policy did not perform good in the taxi problem, but it performs well in the carpool problem, and the state space is also smaller. If we talk about the Q-learning in both of the problems, it is effective in the taxi because the agent is improving and learning something. It is ineffective in the carpool because it takes so long, and also the agent's not learning. That was the references that I've used here, and that was all for my presentation. Thank you so much. Have a nice time.